Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, I would like to finish going through Chapter 6.2 and looking at linear systems with real eigenvalues. In our last video, we ended on page 12 in our guided lecture notes, where we wanted to discuss how you might create what is referred to as a generalized eigenvector for a system with insufficient eigenvectors. So, if your homogeneous linear 2x2 system of first order differential equations has a repeated eigenvalue with only a single eigenvector, then we need to be able to construct a second linearly independent solution, a second eigenvector. To do so, we will find an eigenvector v and a corresponding, find an eigenvalue and a corresponding eigenvector. Then we are looking for a non-zero vector u, referred to as a generalized eigenvector, that satisfies the property that a minus lambda I u equals v. This is not a traditional eigenvector. This is a vector that when you multiply it by your matrix gives you back your first vector. Then our general solution will be of the form presented here. Notice the form of our second solution. It has the same e to the lambda t as our first, but that our vector now is t times our first vector plus our generalized eigenvector. Let me show you this with an example. Consider the linear system presented by this matrix equation. As before, we're going to want to find our eigenvalues. And I like using the trace determinant approach. So notice that for this matrix, the trace of our matrix A, the sum of this main diagonal is 8. And the determinant of our matrix A is going to be 12 minus the negative 4, which gives us 16. So the trace determinant approach says we're going to have lambda squared minus the trace plus your determinant. Notice this polynomial is factorable. And it's factorable in such that we only get one eigenvalue of 4. And now we go look for our eigenvectors by subtracting that lambda, that eigenvalue, off of our main diagonal to produce this matrix. Now again, we're looking for a non-trivial vector that'll give us back the 0 vector. And by inspection, we can find this vector to be the vector 1, negative 2. Go 1 times the first column and negative 2 times the second column. That'll produce the 0 vector. But notice that this is the only vector we get, and we need 2 vectors. So now we're going to look at how to find what is referred to as your generalized eigenvector. To find your generalized eigenvector, we want to look at the equation a minus lambda I u equals v. Now notice that a minus lambda I is the same a minus lambda I that we looked at for our first eigenvector. This is the same matrix. It's the same matrix, so don't use a different matrix. This is still going to look like negative 2, negative 1, 4, 2 times some u vector, which I'll write it as u1 and u2 for its 2 components, And this has to return back our first eigenvector that we found, 1, negative 2. Now remember, when we constructed this matrix is singular, meaning one of these columns is a multiple of the other. And we need to find a combination that produces this eigenvector back. Now generally this can be done by inspection. If you notice your columns, notice how can this vector 1, negative 2 be created from this first column? Or how can it be created from this second column? And generally I believe we can do this by inspection. If we wanted to use the first column, I'm actually noticing that our vector v is, it's a half of the first column, or it's a negative a half of the first column. So one of the eigenvectors we could use would be negative 0.5 of the first column and 0 of the second. Or if you wanted to use the second column, I'm noticing actually our vector v is just the negative of that second column. So what if you did 0 of the first and negative 1 of the second? It turns out that there is an infinite number of vectors that'll work. I just need you to grab one, and generally these are going to be the two easiest to find. It does not matter which one you use, but I'm going to choose to use the vector 0, negative 1 because I don't like decimals as much as whole numbers. So let's use this as our vector u. Now with this as our vector u, we can now write our general solution. Now recall our general solution is going to be of the form c1 e to the lambda t v. This is the first part of our solution. And then c2 e to the lambda t tv plus u. That's the second part of our solution. So here our general solution will look like x of t c1 e to the 4t times the first eigenvector that we found, 1, negative 2, plus c2 e to the 4t, and then remember it's t times your first vector plus your generalized eigenvector, and I chose to use the vector 0, negative 1. This is what your general solution now looks like. However, it's common to rewrite our general solution to not have our second vector be written like this. It's common to rewrite our solution to look more like and I'm going to rewrite this, I'm going to multiply this t into our first vector, and then I'm going to add these two vectors together to write this as t and then negative 2t minus 1. And I think this is the more common way to write your general solution. Okay, now let's think about our phase portrait. What does our solutions look like graphically? Now our first vector, we can still draw this one. It's 1 in the x direction, negative 2 in the y direction. It's a vector that goes through that point. And I like to draw a line now that goes through that point. Draw the best line that I can. And let's label it with its eigenvalue of 4. So notice because the eigenvalue is 4, that e to the 4t gets larger as time goes on, so that any initial conditions starting on this line will always get larger and move away from the origin as time goes on. However, there's a problem with our second eigenvector. Because our second eigenvector is not a vector of constants, I can't draw this eigenvector. And technically, this eigenvector does not appear in our phase portrait, but it does make it confusing to see about how to draw this at your first glance. So to help us with this, let's grab our matrix, our phase portrait plotter. But I need to be able to enter our system of equations in terms of individual equations. So let's go back to our problem and let's rewrite our matrix equation as a system of equations. So here, this matrix equation is equivalent to x prime equals 2x minus y and y prime is 4x plus 6y. So let's enter this system of equations into our phase portrait plotter. Two x minus y and 4x plus 6y. And I'll do my best to include our first eigenvector. Now our first eigenvector went through the pair 1, negative 2. Notice it is moving out like we thought it was, but it's started at point 1, negative 2. I'd like to include the entire line moving from the origin, so I'm going to write point 1 to negative point 2, just so I can get a full line. If you want to draw your other line on the other quadrant, maybe let's put in negative 0.1 and positive 0.2. This represents our straight line solutions. And now let's click around to see what some of these other solutions might look like. Notice depending where you click, you see more or less curvature as our solutions move away from the origin. Let's click some on the other side. Okay. So if I try and clean this up for us, what I think that we should be seeing with our phase portrait is that these solutions tend to be leaving the origin and then they kind of hook around and then move out. And depending on where you pick, you get a different amount of curvature in your solution. Oh, looks like my computer is blanking out for a minute. Okay. Now, because of the nature of our curves, this is sometimes referred to as a almost spiral source. This doesn't really spiral continuously, it just starts to spiral as it leaves the origin. And of course, the leaving the origin part we could identify as because our eigenvalue was positive. If our eigenvalue had been negative, you might be imagining your solution trajectories more almost spiraling into the origin. Okay, I hope this is helpful, and I'll see you in our next video.